Let's get it started. Okay, so here we have the counter today. So last time we talked about latch or register rather, right? We talked about register. Now we'll talk about counter. Okay, so when we say counter, yeah, when we say counter, it counts, right? Okay, let's say if you have two flip-flops, then maximum it can count is 2 to the n. N equals 2, right? So maximum it can count is 4. So now take a look at this picture here down here. So we have two flip-flop, right? The maximum it can count is 4. Okay. So this is the picture of diagram of 2-bit counter. So it can count up to 4. Okay. So a counter is a device that counts clock pulses. So on the basis of type of clock used, we can differentiate counters into two types. Okay, one the asynchronous, and the other one is synchronous. So asynchronous is also called ripple counter. So as the name suggests, synchronous counter is such kind of counter in which the clock pulses are given to both the flip-flop at the same time. So in this case, where is the clock pulse? This is the clock pulse right here. The next clock pulse goes from here. So clock pulse, suppose clock pulse goes like this at the same time, right? So clock pulse goes here and also at the same time clock pulse goes here, then that would be synchronous, okay? But in this case, what happened is we have the clock pulse here in the first one, then second clock pulse is gone, goes from the first one in tandem, right? So first, then the second gets from the first, okay? This is the external source. This guy gets from the external source, and this guy gets from the first flip-flop, okay? This kind of flip-flop, counter is called asynchronous, okay? In the picture, we have shown here the 2-bit asynchronous counter, okay? So it basically consists of the flip-flop, two flip-flops. This is one flip-flop, right? So this is JK flip-flop. Can you please help me? What is the triggering method for this one? Is it negative or positive?
Positive.
Did you see the small thing here?
Oh,
Yeah,
so
yeah, it's negative, right? So remember in the digital electronics, right? We always represent negative by bubble, right? Remember this is NAND gate. You have the
right,
right. This bubble means negative, means NAND.
right.
In the same way, so there is a bubble. It means this works on the negative trigger. Okay, so both of them works at the negative trigger, and this output is connected to this guy. Okay, so this is clock. This is also clock. Okay, this is also clock. This is also behaving as clock.
Right.
So this is external source. The clock gives the signal to the first flip-flop. Then the output of the first one becomes the clock signal to the second flip-flop. Okay, how are the JK terminal? JK terminal is both high in this kind of counter. In this kind of counter, 2-bit synchronous counter. So we keep this J and K both high. This is J, this is K, both are high. Okay, this is J, this is K, both of them are high. Okay, so that's what happens. Now let's see how it works, right? So is this count up or count down? Let's figure that out. Then we'll what is this count up or count down? This is count up. So if you take the if you take the output from here, okay, it will be count up. On the other hand, if you take the output from here, rather, it will be count down. So actually this works as both. Okay, count up and count down. Depends on where you get the output from. Normally we take the output from Q, right? There's no doubt. Okay, this is just the plan B. Okay, this is just the plan B. But if you want to make it count down, then you can take the output from here. But the thing is, how does it work as count down, right? Let's talk about that. So in this case, this is JK flip-flop, and what is the T in this case? T is high. Okay, this is high, right? This is also called T. J and K connected together. That's how you make T flip-flop, right? You can say JK flip-flop or you can say T flip-flop. So in this case, T, if the T is high, right, means J and K, both of them are high. Then what is the nature of that flip-flop? It works on the toggle mode, right? Whatever we call, what we call is toggle mode, right? That's how it works. All right, so let's see how it works, right? Okay, this is the clock pulse, okay? This is given. We have no control over this guy. This is the kind of clock pulse given to the system. So right here, this is given. This kind of clock pulse. Now, when you are given this, when this guy is given this kind of clock pulse, then what happens? So what is the output of this guy here? So I call it Q0. I call it Q1, okay? So what is the output Q0 here? Remember, it works in the negative trigger. Okay, this is negative edge trigger. That's why let's figure out where is your negative trigger here. If this is negative trigger, this is the one. This is 2. This is the negative trigger. This is the negative trigger. This is the negative trigger, right? We have 1, 2, 3, 4, 5 triggers. Now, at the negative triggers, what happens? So what does this do? So this works in toggle mode, right? Because both of them connected to high. This also works in toggle mode. This also works in, both of them works in toggle mode, both flip-flops. So now, so remember this Q0 is 0, right? Q0 is 0. Now right here, this is your initial Q0. So right here, this Q0 is 0 until here, right? Then when it gets the negative trigger here, then what happens? Remember, this guy works in toggle mode, meaning if it were low, now it becomes high until the next trigger. That's the meaning of toggle, right? See, this low becomes high. That's the toggle. Now at this point, again, this is again becomes, help me here, toggle, right? This negative trigger again, toggle meaning the opposite of whatever we have now. So we have 1. So when it toggles, then it gets 0 here. Okay, so up to here you get 0. Then you get negative again, you get 1. Okay, the negative again you get 0. Then here you get toggle again. Okay, like that. This is how it works. So far so good. So this is your Q0. You know, you can take output from here. This is your Q0. This is your Q1. Now, how about Q2 now? Now, how about this guy? Okay, let's talk about this guy here. So how does this work? Now, this green thing is the clock now, right? So this is clock. So meaning this is the negative edge. This is the negative edge. Remember, because this Q0 becomes the input to the next flip-flop. See that? That's why this is my trigger now. Okay, so there are 2 edges here in this. So I have 1 edge here, there's another edge here. Okay, so in the beginning Q1 is in 0 state. So up to this point nothing will happen, right? Okay, so nothing will happen. When it triggers, then what happens? Toggle, right? This also works under toggle on the toggle mode. Okay, this works on the toggle mode. So that's why, meaning this low becomes high until the next trigger. Then again at this point it toggles, right? Right, question here. I think I'm done with my explanation. Question, please.
I think we're good.
Okay. I have a question then. If you don't have question, I have a question for you. So how does it work as a counter? You didn't ask me that. Okay, we understand how it works, but how come it is a counter now? How do you know this is a counter? I know this is how it works, but how come it is a counter?
Would it be reading the alternations between 0 and 1, since it looks like the Q0, it's just going 0, 1, 0, 1 in that pattern?
Exactly. So yeah, so this is how it works. So this is your least significant bit, LSB. This is your most significant bit, MSB. Okay, so here, so at the time this is 0. At the time most significant is 0. What is the least significant? At the time most significant is 0. What is your least significant? 0. How do I know? That's how I know. At the time least significant is 0, most significant also 0, because this is my most significant, this is my least significant. Now at the time this guy becomes 1. So what does this guy become?
It's
It
still
would, sorry, it would still be 0.
It is 0, right? Oh, you know what? I made a mistake. So this should be LSB. This is MSB. Okay. Okay. So when LSB is 0, MSB is 0. So this is done, right? Then when MSB is 0, MSB is 0 and LSB is 1. So you get 0, 1, right? And this is MSB, this is LSB, right? Okay. So when you display, you have to switch the order like this. When you display, you have to switch like this. Remember your SSD, you have to put the SSD in this way, okay? This is your SSD, right? 7-segment display. Okay. So now, so how do you get 0 and 1? See, this is 0, this is 1. Look at that. At the time, this guy is 1, this guy becomes 0, right? How do I know? From the diagram here. Look at this, from the diagram. So 0, 1, right? 0 and 1, MSP 0, LSP 1, which is 1, right? Which is 1. Now at the time, LSP is 0, MSP is 1. MSP is 1, LSP is 0. Then what do you get? 2. Now at the time, LSP and MSP both 1. What do you get?
3.
1 and 1, 3. So this counter cannot count more than 3. Okay, why? So it counts 0 through 3, right? 0, 1, 2, 3. Because you have just 2 counters, so 2 to the n equals 2 to the 2, right? So this 2 is number of counters, so which is 4. We have 1, 2, 3, 4. You cannot have more than 40 steps. Now do you understand how it works as counter?
How would you make a higher counter?
Yeah, this is how you can make that. Or higher counter meaning counting bigger than this.
Yeah.
Yeah, you have to have this flip-flop again and again and again and again and again and again and again. You have to repeat. So if you have 3 flip-flops, then you can count up to 0 through 7. Okay, if you have 4 flip-flops, you can count up to 0 to 15. So you have to connect them in tandem like this. Did I answer your question?
Yeah, that was good. Thank you.
All right, thanks. Thank you for the question. All right, now, so we proved that this guy is a up counter, right? Similarly, if you take from if you do the opposite thing right here, right? So this guy, you know, from the Q prime. This is the Q prime, right? So will this be down counter or up counter? See, you start with 1, right? See, you start with 1 on 1. So you start with 1, 1 is 3. Then you have 10, right? You have 10. No, sorry, 1, 0, 10, right? For the other ones. Then you have 0, 1. Then you have 0, 0, right? So it will go downward. So if you take it from here, rather, instead of up counter, you get the down counter. Make sense? Okay, now one of the uses of this guy, this asynchronous counter is, obviously it's counter, so it counts, right? So you have another use of this counter also. Not only counting, we can also use this guy as frequency divider. Okay, let's see how it works. It's the same counter again. So it's now So how does it work? It's the same diagram. Okay, I just copied and pasted here. So it's the exactly same diagram. Now, how does this act as a frequency divider? What did I say? Frequency divider. Frequency divider. It means, so whatever frequency we have, suppose this is the frequency of the signal here, I will call it, I don't know, what is the frequency of the signal? I don't know, 8 hertz, right? Let's say frequency of the signal here is 8 hertz. Then what is the frequency of the signal here? 8 divided by 4. This 4 coming from 2 to the n again. So 8 divided by 2 to the n, where n is number of counters. So 2 to the 2, 8 divided by 4 equals 2. So if you have frequency here, 8, then you'll get the frequency here equals 2. So let's see how it works. Now you have to help me here though. So is the frequency of this guy higher or lower? What is the maximum frequency? Which signal has maximum frequency in these three signals? Can you help me here?
Would it be clock?
Clock has the maximum frequency, right? So what is frequency? Frequency is number of cycle per second, right? Number of cycle per second. Suppose so for the signal to, so in one cycle, so let's say this is the 1 second period, okay? We get this many signals in 1 second. Okay, this is 1 second. In 1 second, how many signals do you get? 1, 2, 3, 4, 5. I don't know. Let's call 5. 1 second up to here. So what is the frequency of this guy? 5 hertz. Okay. So what is the frequency of this guy? Let's say you know what? My life will be easier if I consider up to here. 1 second. In 1 second, suppose this is what you get in 1 second. So then frequency is 4 hertz, right? 4 hertz. Now what happens here? What is the frequency here? Can you help me? What is the frequency here?
Would it be 2 hertz?
2 hertz. Okay. How about here?
1 hertz?
Not even 1 hertz. This is half. Right? This is just 1 cycle. See, half cycle. See that? Oh. What did I say? Yeah, 1 cycle. Should be 1 hertz. You're right. So why did I say 4? Divide by 4 then here. Oh, okay. Oh, okay. Because this is my original frequency, right? So this is the frequency you sent in. This is your input frequency. So this is your output frequency. So what is the relationship between input and output? Divide by 4. That's what I meant.
Oh, that makes sense.
It didn't make sense to me either. So I was what? Yeah. So that's why this synchronous counter also is a frequency divider. Suppose you are high frequency signal, right? You have a high frequency signal, right? Then if you want to divide the frequency, then what kind of counter, you use this kind of counter. So this counter also acts as frequency divider.
So like, say in like a computer, this was running, how would it account for the false states generated by not being synchronous?
So how does it generate the false state?
It says, as a consequence, false states may be generated.
Oh, okay, this guy, right?
Yeah.
Hey, because okay. Okay, so what I meant is this. So this guy and this guy, will the output appear at the same time? So you have to wait a little bit to settle to the new value, right? So whenever you have new value here, this is still in old value. Because this guy goes here, then it gets the value already. But this guy will get this value once this guy goes into it. So this guy has to wait a little bit to settle the new value. Okay, so that's why, you'll see some false state before this guy settles to the new state. That's what I meant. And Austin, I'm afraid I answered your question.
You did.
Okay, thank you. All right. Okay, now let's do the synchronous counter. So for the synchronous counter, so this is very simple now, because once you understand the synchronous, let's do this here, the synchronous, meaning it's the same thing again. We have two counters, two flip-flops. I call it flip-flop 0, I call it flip-flop 1. And again, these are T flip-flop, right? So J, K connected together, right? So J and K connected together. That's how you make T flip-flops here. Then the first one is exactly as before. Remember? In the previous one, in the asynchronous, in the case of asynchronous, we had both of them high, right? But here, we have made some changes. So in this case, the first one is high, but second one, because we don't need to supply the clock from here. Remember, we don't have to supply the clock from here, like in the previous case, because both of them are getting the clock at the same time. That's the meaning of synchronous, right? At the same time. So that's why, so clock is not a problem. Then we use this guy, Q0, as the input to FF1. So when you do this guy acts as a synchronous counter. Okay, so this is in toggle mode, right? This acts in toggle mode. So toggle mode meaning this, right? This is the toggle mode. And the other one here, another one here either works in toggle mode or hold mode, right? If Q is 0, then there is no change, hold. If Q is 1, then both of them, J and K, both of 1, so it is a toggle. So this guy is just toggle. This guy is toggle, or hold, T or H. These are two modes. Okay. All right. So let's see how it works. So this is a clock signal. Clock signal is given. So this clock signal is given. Okay, this is given. We have no question here. Okay, we cannot. So we cannot raise any question here. This is given. Now based on this clock, now you have to figure out Q0 and Q1. What is Q0? What is Q1? Let's do that. Okay. So let's do the Q0 first. Okay, so the clock is low, right? Clock is low. Is this negative or positive trigger?
Positive.
Positive, right? This is positive. Thank you. So this is positive trigger because we don't have bubble here. So meaning this guy works right here. Oh, guys, I forgot to tell you something. Okay, so this is the thing we'll be doing. The next lab will be using this guy as frequency divider. Okay, I forgot to tell you about that. So this is the next lab. So this is given, right? This is given. So we have 4 locations where the change will occur. Okay. Now let's see how this Q0 works. So at this thing, at this when the signal goes low to high, so what happens to this guy? This is Q0, right? So this is always high, means toggle, right? So it was low, that's why you have high up to here. So now, how about this guy? Well, I'll go this Q0 and Q1 together, side by side. So how about Q1? Why did I decide to go side by side? Because I don't have to wait for the clock. I have given the clock at the exact same time. That's the meaning of synchronous. That's why I can get this guy and this guy at the same time. You don't have to wait for the false state, right? Okay, remember in the previous one, we'll see the false state. But here we don't, because the false is given at the exactly same time, synchronously. So now I got Q0 up to here. How about Q1? Because pulse is already there. So what will be your Q1? Will that based off this 1 or this 0? Because this Q1 based on Q0, right? Now Q0 has 2 values. We had 0 here, we have 1 here. So this Q1 is based on this guy or this guy. Because the Q1 appears right at this moment, because remember this is the exact same, they share exactly the same clock. Whenever the Q0 happens, Q1 also happens. They happen at exactly the same time. Both of them happening at the exact same time because they share the clock. Okay. Now can you help me here? Can you help me here? So this Q1, so the Q1, the output for this flip-flop, this output based on Q0, right?
Mm-hmm.
Okay. Now, When the transition occurs, there are two Q zeros. One is 0, the other is 1. See, during the transition, right? One is 0, the other is 1. So do you take this guy or this guy? That's what I'm asking. Will the Q, do you consider Q0 to be 0 or 1? This or this?
0,
Why?
because it's the value that the second set of flip-flops would have first in that next clock time.
Exactly, exactly. So because, yeah, so let me, that's very good answer. So because by the time this guy receives the clock, this also receives the clock. Okay, but for Q0 to change from 0 to 1, right? For Q0 to change from 0 to 1, it takes some time. So, but the thing is, both of them are getting the clock at the same time. They have to do the work at the same time. See, they have to do the work exactly at the same time, right here. Both of them has to work right here, right at this moment. Right at this moment, both of them has to work. Otherwise, they will have to wait until this point. Okay, so they don't do that. They don't wait. They are not, you know, they are not human, right? They just do whatever they are supposed, you know, told to do. They are the slave, right? So that's why they will do exactly the thing that you told them to do. So right at when the signal or clock signal goes from 0 to 1, you know, both of these guys work. Okay, but the thing is, so they have to work at the same time. So by the time this guy gives Q0, okay, this already gives you Q1. This already gives you Q1 before the new value of Q0 appears here. Q1 is already there before the new value of Q0 already is here, because it takes some time to process to new value. That's why we have to based on this 0. Even though it changes to 1, we have to based on this 0. Meaning, so this changes from 0 to 1, but this guy still is 0 because it is based on this 0, not this 1. It takes time for the change to happen. So that's why it stays 0. It stays 0 until the next, what is my next thing? This is next, until the next thing here. It was 0 and it remains 0 until the next thing. Now right here, what will happen? This works in toggle mode, right? Toggle meaning it was high, now will be low up to here. But how about this guy? What will this guy do? So
It'll rely on the 1.
why?
Because it had the 1 first.
Yes. So remember it changed from 0 to 1 to 0. Now it will rely on 1. So now your Q0 changes from 1 to 0. Next clock, 1 to 0. Meaning it has to rely on the first one again. So what is the first one? 1. So 1 is there, 1 is there, 1 is there. What is this 1 and 1? Toggle mode. Meaning now it has to toggle the mode. Okay? Toggle meaning it was low, right? It was low. It has to go high. This is toggle mode. let's see how it happens right at this moment, right here. Right here, what happens? Guys, I'm lost. Help me. What I'm trying to say. Right here, there is a change from 0 to 1 again, right?
Right.
Because
Q1 would rely on the 0.
now the Q1 will rely on 0, right? So meaning this is 0, 0, meaning no change, right? 0, 0 is no change, meaning it will stay the same again. No change, high. It was high, remain high. That's called no change. Okay. Again, there is a, there is a clock signal. Then it works on the toggle mode. So this high becomes low. But this guy will based off this one, which is toggle. So that's why now it started having low, because it was high, now it's low. Guys, is there any question? Question here, please.
So how would we get a scenario where it's either set or reset? Because so far we've either only gotten no change or toggle for
No.
Q.
No, our goal is not to make set or reset, right? So we have to use the value according to our goal, right? What is our goal right here? Our goal is, that's a good question, Bridget. So our goal is to make a counter, right? So now let's see, did we have a counter? If we have a counter, we accomplished our goal. So we don't have to worry about reset and set. So see, we have 0, 0, we have 0, 1, we have 1, 0, we have 1, 1. We have a counter.
Okay.
0, this is 1, this is 2, this is 3.
Gotcha.
All right, good.
Thank you.
You're welcome. Okay, now let me introduce some new concept, then move on to the next slide. So next topic, okay? So this is the background for the next topic. Okay, so here, I don't have to even, you can just read it and it will be just fine. Okay, so you have the, in this case, I have a D flip-flop, right? See, this is my D flip-flop. This is the enable switch, enable line, and you have Q and Q prime or Q bar. Then you have two more terminal here. One is pre, which is preset. Pre is preset, and CL is clear. Okay. What is my clear? Yeah, clear. So sometimes what you want to do is, okay, you wanna have 0 here right away. You cannot wait for the signal to change, right? You cannot wait for the change to happen. You want 0 right away. Then what do? You just push this preset button, or give the preset to 0 ground, right? Because this works as a low active low, okay? Meaning this becomes active when it is low. That's what is the meaning of active low, okay? So when preset is active, that active meaning your Q is 0 right away. On the other hand, if clear is 0, then you get, what did I say? I said the other way around. Sorry. So when you said clear, you get 0. Okay. When you push preset, you get 1 right away. Okay. It's the method of getting 0 or 1 right away. Meaning it overrides all the other whatever data we have here. Okay, so you can either choose preset equals 0 or clear equals 0. What happens if both of them are 1? If both of them are 1, what happens? It means none of them are active, right? Meaning your flip-flop works normally. How about both of them are 0? So when I said 0 before, right, I said either or. Either this is 0 or this is 0. Now what I'm saying is both of them are 0 at the same time. That doesn't happen, okay? That's forbidden. If you do that, you don't get anything. That's illegal. Okay, now let's use the clear. Sometimes we use preset, sometimes we use clear, okay? So now I'm going to solve one problem, problem 5.3 from the book. In this case, I'll be using clear function. To make this happen. So what I'm planning to do, I am planning to use a positive age trigger T flip-flops. It's the positive again, okay? With clear and preset inputs, you have both there, but you can use either or, okay? Either use clear or preset. Now I'm planning to use clear. Design a synchronous decade counter. Decade. So what is the meaning of this? Means 10, right? It counts up to 9. 0 through 9, 10 in total. Then resets to 0. After 9, it resets to 0. So how many flip-flops you have? 2 to the 4. So we have 4 flip-flops. It can count up to, help me here, 16. It can count up to 16, but that's not your goal. Your goal is to count up to 9 and come back to, again, 0. After 9, you come back to 0. If you had to make it counting up to 16, you don't have any problem here because you do exactly the same thing here. Exactly like this. Exactly like this. But you have to add 2 more exactly. Make the exact copy of these guys. 2 more. 3, 4. So this count up to 2 to the 0, 2 to the 1. This can count, this plus this can count 2 to the 2. This plus this can 2 to the 3. This plus this can count 2 to the 4. So 16, done. You just add 2 more and you're done. But the problem here is not that. Our problem here is you stop at 10, you stop at 9. So how do you make it happen? That's the thing. So did you guys understand what the question is trying to say?
Yeah.
Nice. Now, so we begin with 4 because we have to count up to 10, right? So 2 to the 3 in, just 8. We are too short, right? So that's why we have to go 2 to the 4, which is 16. But we have to stop at 9, 10. So 0 through 9. So 2 to the 3 will stop at 7. 0 through 7, 8. And 2 to the 4 stop has 15. 0 to 15, 16. Now we have to make it stop at 10. Stop at 9. So it can count just 10 digits, 0 through 9. So how do you make it happen? So I don't think anything else is the problem. The problem is how to stop, right? That's the problem. So where should it stop? So what is your 9? 9 is what? 1, 0, 0, 1 is 9. This is 2 to the 0. This is 2 to the 1. This is 2 to the 2. This is 2 to the 3. So 1 times 2 to the 3 plus 0 plus 0 plus 1 times 2 to the 0. So this is 8. This is 1. So 8 plus 1, 9. So we have to go up to this. What is the next one? What is the next one? This is 9. What is 10? 1,
0, 1, 0.
0. Yeah. So what happens is, okay, now this guy has to be changed to 0 right away. This has to be 0, 0, 0, 0. So we have to count up to 9. Whenever we go to 10, boom, 0, 0, 0, 0, right away. How do you make that happen? Meaning right here, you have to hit the clear, right here. Make it clear, meaning everything changes to 0. Clear means what? Everything 0, right? Right away. This changes to 0, then go back to again. Start from 0 again. 0, then 1, then 2, goes all the way to 9. Then when it sees 10, boom, comes back to 0 again. Then 1, 2, 3, again and again, repeats the same process. That's what our plan is, right? So how do you do that? The thing is, so this is my S0. Okay, this is your, so what do we need? 101, 1010 has to be 0, 0, right? Guys, any comments? How do you make that happen? Remember the parametric design? Yeah, go ahead.
I have a question about the third bullet point down. It says when clear equals 0, we get Q equals 0. So does that mean when clear is 0, that's when it clears the screen, like it clears the numbers, or does clear have to equal 1? Like, is it a positive or a high or a low input?
This is low active, okay? So
Okay.
I should have put their bar here. Sorry. Good catch. This is low active, okay? Did I answer your question?
Yeah, definitely.
Okay, thank you. Now, how do you make this happen, guys? So let's see how this is the problem. Can you help me solve this problem? So right at, what is my, this guy is 0. This guy is 0. This guy is 1. This guy is 0. This guy is 1.
So then we'll have to make it so that when S equals 1, or when S3 equals 1 and S1 equals 1, that it makes clear equals 0.
Yeah, we have to clear that and make it 0. So how do you make it happen? That's what I'm asking. But when the system is set, right? It cannot go inside the system and it can keep changing. It's set, right? It has to work on its own. So in the lab, you can set it to 0, right? But when the system is ready, so suppose you have a decade counter. Once the counter is ready, you cannot change it. That's why it has to function internally. You cannot change the clear. The device has to clear itself. How do you make that happen? Did you understand my question?
Mm-hmm.
Yeah, so how do you make that happen? You know what I do? I multiply this together. So I will use the NAND gate here. I use the NAND gate. It's a 2-input NAND gate. What I do is I get the one from here. I get this guy from here. Okay, when I reach this, okay, I'm talking about the very last one. Okay, but the thing is, it has to work 0 through 9 also. Okay, I'll convince you for that. Okay, but for this time, let me say this is my solution. For the 10, this is my 10, right? Let me make it working for 10. Then I have to make sure you understand how it works for 0 through 9. Okay, this is part 2 now. Let me discuss my part 1. When it becomes 10, meaning 0, 1, 0, 1. What I did here is I connected this one to here to the NAND gate and this one to here to the NAND gate. What is the input to the NAND gate?
1, 1,
What is the output?
0.
0. So now this 0 goes everywhere. This 0 goes here, this 0 goes here, this 0 goes here, this 0 goes here. Because remember, this is connected, all connected. These are all connected. So this 0 goes everywhere, meaning this guy will be 0, this guy will be 0, this guy will be 0, this guy will be 0. This is what we want, right?
Right.
But the thing is, does it still work 0 through 9? Okay, so suppose we have 0, 0, 0, 0, 0, 0. In that case, 0 through 9 it shouldn't clear. Okay, only when it reaches to 10, it should clear. So at 0, 0, 0, 0, what is your thing here? This is 0.
Mhm.
So what is the thing here?
0,
0. So what is 0 and 0?
1.
So you get 1. So let's see, we're talking about which one? We are talking about, help me here. Second and the last, right? So here, second and the last, second and the last, second and the last. I have to make sure it works for everything. Second and the last, 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 second and the last. So 10 is 1, 0, 1, 0. Okay, second and last. So we already know this works, right? Now how about here? If the input is 0, 0, what is the output? 1. What if the input is, what happens if the input is 0, 0? See, it's again 0, 0. 0, 0 is not a problem. We already saw that. How about 0, 1?
It would be 1.
It will be 1 again. That's not a problem. 0, 1, that's not a problem. 0, 0, that's not a problem. 0, 0, that's not a problem. Multiply these together. 0, that's not a problem. 1 and 0, that's not a problem. 0 and 1, that's not a problem. 0 and 1, that's not a problem. So we checked 0 to 9 also. It doesn't bother. Okay, this is our solution. Guys, does it make sense?
Yeah.
Good.
Mm-hmm.
So we might have similar problem in the homework. Okay, so this is called pragmatic design. Okay, so you remember we did one problem last time, number 14, to make the decade counter from the binary counter to BCD counter, remember? From binary to BCD, right? This phrase is very, very important in digital world, pragmatic design. If it works, works. Okay, so no matter what, no matter how you make it working, but if it works, works. Okay, so that's why I call it pragmatic. So we checked everything one by one. It works fine. All right. Now let's talk about state machine. State machine meaning the machine having different states. So our counter had 0 through 0, 1. The very first counter had this, right? Okay. And the counter, right? Homework problem. This is also a counter, right? 5.3. How many states are there? 0 through 9. So this is 4-state machine. This is 10-state machine. Okay. Or we have a nice phrase for that. We call it okay, mod 4 counter or mod 10 counter. This is what we call. A state machine is a digital device which traverses through a predetermined sequence of states. So we know what it will going to go through, right? It is going to go through 0, 1, 2, 3. It is going to go through 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's predetermined. Okay? And predetermined sequence of states in an orderly fashion, right? So it goes in order, like 0 to 1, 1 to 2, in that way. So this kind of machine are called state machine. So output of the state function, state machine is function of input and current state. Please keep that in mind. Is input and current state. Okay. So for instance, if you want to start with this for this, right? Let's talk about mod 4. So what will be the input? You have to start with the 0, 0, right? It will start the so this is what I'm trying to say. So if the current state is 0, 0, 0, 0, then the next state will be 0, 0, 0, 1. Okay, that's what I'm trying to say. Oops, this is just 2, 1, right? Okay, 0, 0. Then you have 0, 1. The next state will be. It depends on the next state, depends on the current state. Okay, that's what I'm trying to say. And so it depends on the input, definitely. It depends on input also. You have to choose the input wisely, right? Remember, that's what we did here. We have to choose the input wisely. Input of this guy. Okay. And also input here also has to be chosen wisely. So input and current state, these are the two things you have to keep in mind. Okay, you have to choose input and current state, very properly. Okay. All right. So one example would be and another example is this. So you have seen this, right? So how many flip-flops do you need for this guy? You wanna devise traffic controller. How many flip-flops do you need? Suppose this is your project. I gave you the project, design a traffic controller, and gave you the flip-flop. That will be the next lab. So not the traffic thing, but if you want, you can do that too. So how many flip-flops do you need for this one? Any idea?
4.
Yes, you can, but I think 4 is way too much.
So then 2.
2, right? Because how many states do you need?
You need 4 states.
4 states. So you need 2 to the n flip-flops. So in our case, 2 to the n equals, and its number of flip-flop. 2 to the n equals 2. You need, so 4 states can be accomplished by using 2 flip-flops. Right, so let's make a modulo 6 counter. Okay, so you might have a question, homework question about this. Okay, so let's make modulo 6 counter. So we did using modulo help me here, 4, right? But the thing is, we haven't. This cannot go to production. Okay, this guy cannot go to production. So how do you choose this thing? So we haven't determined this guy here. This has to come from the output. Okay, this has to come from the output. So you cannot do this. Okay, so now, okay, I'll come back to it. So let me do this first. Okay, so what I'm trying to do here is, how much time do we have? 4 minutes. So I think I can finish some of it. So what I'm trying to do here is, I'm trying to make a modulo 6 counter, meaning it counts from 0 to 5. So how many do you need? How many flip-flops? 2 to the 2 is 4. 2 to the 3 is 8. So 4 does not work because I have 5. I have 6, right? So we have to use 3. That's why I have this 3Q for. So QA for A flip-flop, B for B flip-flop, C for third flip-flop. Okay, I have 3 flip-flops there. All right, so again, I'm using T flip-flop, right? Now I'm going to introduce here something new. Why do I need this? Once you understand once I find the solution, then you'll understand it. Okay, and I'll explain why this needed. So this table is called excitation table. This kind of table. So excitation table meaning, so you know the initial state of QA. What is the final state of QA? Suppose what are the combination for initial and final state for QA? Your QA could be 0. The initial state could be 0, right? This is the one. The final state could be 0. So initial 0, final 0. What is the next combination? Initial 0, final 1. Initial 1, final 0. Initial 1, final 1. These are different combination of initial and final state for QA. Similarly, you have the similar thing for QB. Similarly, you will have similar thing for the QC. Does it make sense? So when Q0 is 0 and final state is 0, what should be the value of T in that case? Can you guys help me here? It means your T flip-flop is hold or toggle mode?
Hold.
Hold, right? It's hold mode. So when are the hold mode or no change mode? What should be the value of T for that to happen?
0.
That's what 0 is. Okay? If Q is 0, initial state is 0, final state is 1, then what happened there? Can I call it toggle mode? If the initial was 0, final is 1, I can call it toggle mode, right?
Yeah.
For the toggle mode to happen, what should be the value of T? 0 or 1?
1.
1. That's why I have this 1 here. So then again, suppose you have 1, then changes to 0. Again, there is toggle, right? So then you have to have 1 again. Suppose you have both initial and final state 0. For that to happen, you have to have T equals 0. Do you understand this table?
Yeah.
So this is called excitation table because I'm exciting from Q to Q plus. initial state to final state. This is called excitation. In electronics design, an excitation table shows the minimum inputs that are necessary to generate particular next state when the current state is known. Okay, actually this is the excitation table, sorry. This is not, we based on this, okay, we rely on this guy, but this is not complete yet because this is the general rule, but we have to talk about all those three flip-flops, right? QA, QB, QC. The detail is here. Okay. Do you guys have 1 minute? I'll finish it in 1 minute. Okay, so we rely on this guy to figure out this table here. Let's do that. Okay. Now help me here. Now, what are the three possible combinations of QA, QB, and QC? You have three flip-flops, right? So this is your QA, this is your QB, this is your QC, the output. So your QAs can be 0, QB can be 0, QC can be 0. This is one of the combination. Next combination could be 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. We don't have more than that, right? So these are the combination we have. But the thing is, we don't need more than 5. Okay, we don't need more than 5. So that's why after 5, see, when the initial state is 0, 0, 0, right? This is 0, 0, 0. Then what is the next state? From 0, 0, 0 to, we have to go to the 0, 0, 1. That's the final state. Meaning 0 has to go to 1. Then 1 has to go to, it has to change to 2. 2 has to change to 3. 0, 1, 1 is 3, right? Then 3 has to change to 4. And 4 has to change to 5. And 5 has to reset. 6 has to reset. 7 has to reset. That's how you make the modulo 6 counter. Okay? Let's complete this table, okay? So 0, 0, 1, when this is 0, when Q0 is 0, sorry, QAT is 0, QAT plus 1 is 0. When both of them are 0, what do you get? What is the value of T? 0.
0.
So when Q0 is 0, QA is 0. What is the value of T? 0. 0 again. When QAT is 0, QAT plus 1 is 0. What is the value of T?
0.
What is the value of Q? When QA is 0, the QAT is 1.
1.
This is the case, right? That's what I have. See, I did the same thing again and again. Similarly, I do for B also. This guy and this guy. Similarly, I do this guy and this guy also. And I get these two column also. Okay, so I'll do this. I'll finish this tomorrow, next week rather.
Okay.
Unless you have any question, I'm done for the day.
Thank
Have a
you.
good
Bye-bye.
Have a nice day.